right, good morning. So we will discuss this question today. I am nowadays concentrating on semiconductors. It's a tough topic, and many students are left with a lot of doubts in this chapter, which I am clearing now. This is a question from NCERT Exemplar, CBSE course, but if you're a student of AP Physics or SAT Physics or any other board in the country, this will help you understand light emitting diodes. So the question is, why the elemental semiconductors cannot be used to make visible LED? So I'll give you the answer to this in the form of a diagram. See, elemental semiconductors, these are germanium and silicon, right? The most versatile semiconductors in the world, right? Now let me just give you a high level picture of how the LED works. Okay, so and then we'll get into the details of this explanation. Okay, so I'm drawing a PN junction diode, okay, which is what an LED is. So LED is a PN junction diode, and the you have a junction as usual, right, which is where the P and N are connected, and on the both sides what you have is, so you have this P, you have N, and what, so this PN junction, right, what you do is you forward bias it, right? So you forward bias this. So LED works in forward bias, by the way, okay? And okay, so this is your LED, and I'm doing a forward bias. I'm connecting P to the P, okay? And I'm doing it right in front of you so that you can memorize this, right? You yourself will be able to solve this. If you just see diagrams which are pre-made, you don't understand how the diagrams are to be made. So let's try to understand. So the positive terminal is connected to the P, and this is your junction, right? So this is your junction, right? So this is your junction, and this is your depletion zone that gets created, right? So there's a junction potential here. And once you forward bias, what happens is the holes on this side, they start traveling, right? So this dopant is a trivalent dopant in P, right? Something like a boron or maybe aluminum. N side is more pentavalent impurity or dopant, and the electrons from N side move towards this side now, which means what you have is a flow of current, right? So the LED is forward biased, so the LED is forward biased. Okay, this is something we've already discussed. Current starts flowing. Now there are two situations. You make this LED. Okay, let me just tell you. So when this current flows in the depletion region, right, which is this region, you have something called as recombination, right? A recombination happening. So recombination happens. Recombination happens, which means, you, if you understand the acceptor level and the donor level energy levels, right? So N is donor level, right? And the P type is the acceptor level. So the electrons can jump very easily in the case of donor level to the conduction level very easily because the gap is very small. So you can go back to my videos where I've explained you how does an N-type semiconductor work, and you can see that the conduction band is here and the donor energy level is very close to that, right? And then you have, of course, the forbidden gap and the valence band, right? So this is your valence band, the valence band, and then, right? So that is what we discussed. So this is your donor level energy, donor level energy, donor level, all right? And this could be phosphorus, for example, right? And a phosphorus. So the electron can easily jump to the conduction band from here. So this is your energy gap, right? So this is your energy gap. Okay. This is the valence band. This is the conduction band. Now, why I explained you this, because when recombination happens, this phenomena is where the electron in the conduction band, electron in the conduction band falls back to the donor level energy. Okay, so it loses energy because it is entering the process of recombination. Okay, and the p level, which is the hole, right? So the hole which is entering, so a lot of holes on this side, you remember, right? P side has a lot of holes and this has a lot of electrons. Also undergoes a similar process, but at the acceptor level, right? So the electron in the level, which is at the acceptor level electron, falls back to the valence band, right? The acceptor level is very close to the valence band. The recombination is the process of annihilation, which means destruction. The holes and electrons are meeting in this region. Let me just tell you the region in which the holes and electrons are meeting. Okay, so this is the region where the holes and electrons are meeting. As they pass through and enter, the junction, they recombine here. The process of recombination, where the energy levels of the electrons drop, from the levels I just explained you. And I don't want to extend this video a lot because I expect that you understand the energy levels of a donor, the energy level of an acceptor, and how a P and N junction works. That's an assumption I have that you understand. Now, when the hole and the electron are entering the depletion zone, the process of annihilation happens and there is a release of energy. Okay, so the release of energy happens in the form of a photon. This is the way a LED works. Okay, I hope this is clear in your mind. The recombination is happening in the depletion region, which is highlighted here, and you have a photon getting released because the energy gets released as the electrons fall to the lower energy level. Now, when this happens, in the case of elemental classic, the most versatile of the semiconductors, this happens in because if you have a PN junction diode, which is forward bias, the way I've just forward biased this. In the case of forward bias, the photon is getting released in the case of silicon and germanium. So photon is getting released. Photon is getting released. The problem here is that this photon, which is getting released, is not in visible region. Okay, this is the biggest problem. You can't see it. And an LED should release visible light. Okay, this is the way this works, that the LED has to work and release visible light. And therefore, if you use elemental semiconductors like silicon and germanium, these don't work, right? Because the visible light is not available. The some frequent wavelength is available associated with this photon. It's not visible. Then how do you overcome this? The way you overcome this is that you have to get some fancy material, right? So if you look into some fancy material used for making the LEDs, so use some fancy material, do some engineering, and replace the elemental silicon and germanium with some fancy semiconducting material. You will see the examples of gallium, arsenide, and all that. So those are the ones that release a visible range photons. Okay, they release the visible range photons. This is a reason why you should not use silicon and germanium and rather use fancy material. This is if somebody says, what is the difference between a normal PN junction diode? Okay, what is the difference between a PN junction diode normal versus an LED? This is the basic difference. An LED is made up of fancy material so that you can get some frequency in the visible region. But if you talk about PN junction diode, the photons are still released, but they are not part of the visible range. They're part of the invisible range. You can't see it. Okay. So I hope this made sense to you. Please do understand how an NNP semiconductor work. What is a dopant energy level? When I say recombination happens, a photon gets released, there is a loss of energy, right? So the electrical energy or the energy is getting converted into light energy. Okay. So this channel has 2000 videos. Explanation is given to the concepts which students generally find very hard to understand. And therefore, it is important that if you're reading your books, that may not be sufficient. This channel will complement and give you that insight which is even missing in the books. The articulation will, hammer the point across in your mind, and you will never forget the concept. So I hope this NCERT exemplar answer is well understood by you. Thank you very much for your time, and please wait for my next video.